Hello, everyone. Good morning, good afternoon, or good day in general. Welcome to our meteorology class again. And today we are moving on to our fourth topic. And as what you can see, we're going to talk about the cloud development and precipitation in general. This is our main topic for today. And for our subtopic, uh, we have the atmospheric stability and adiabatic processes. And we also have the cloud formation. And we're going to talk about the precipitation processes and types and the precipitation measurement as well. To start with the adiabatic processes and the atmospheric stability, we're going to define first, or let's what is adiabatic process or what are these processes? When we say adiabatic, it has something to do with the temperature change without removal of the heat energy. So, okay, we define the adiabatic temperature changes. It's officially defined as the temperature changes due to increasing or decreasing pressure rather than the addition or subtraction of heat energy. So this means that there is a varying temperature or the difference or the changes in temperature, but there is neither addition nor subtraction. There is no removal or adding of this heat energy. That's why it's called adiabatic temperature changes, because the temperature changes was a result from the changes in pressure and not from the addition or removal of the heat energy. So you can see a balloon here. Let's say that this balloon is a parcel of air. To give an example for our adiabatic processes, the meteorologists call this imaginary volume of air a parcel. So inside the balloon, there is a volume of air, right? So let's call this a parcel of air, and we assume that it acts independently of the surrounding air. And it is also assumed that there is no heat transferred into or removed rather outside of the parcel, because we are talking about the adiabatic process. So when the air is actually compressed because of the pressure, it warms. And when the air is allowed to expand, it cools. So this balloon, a parcel of air, behaves much like an actual volume of air moving up or down in the atmosphere. And if you recall that when you move up and down in the atmosphere during our first topic, there was or there is always the pressure decrease with height. So anytime a parcel of air, this yellow parcel of air, this volume of air moves upward, it passes through regions of successively lower pressure. As a result, this rising air or the ascending air expands and cools adiabatically. Again, there is no removal or addition of heat energy, but just because of the pressure changes, when the air ascends and it expands, it cools down. That's what we call the adiabatic cooling. So for the unsaturated air, let's say, because there are saturated and unsaturated air. I think we've already mentioned these terms before in the previous topics, the saturation or unsaturation. So later on, we're gonna review what really is saturation. But for now, unsaturated air cools at a rate of, let's say, 10 degrees Celsius for every 1,000 meters or 5.5 degree Fahrenheit per 1,000 feet as it goes up, right? As it goes up 1,000 meter or 1,000 feet, let's say. And this unsaturated air cools at a constant rate. And this is just an example of what I've mentioned. It's not just also the going up, but also when air goes down and it undergoes the increasing pressure and it's compressed and heated. So there's also the temperature change. And this rate actually, as mentioned, the 10 degrees Celsius rate that changes in temperature due to pressure rather than the loss or addition of heat energy, this is what we call dry adiabatic rate. It's called dry adiabatic rate because dry, that refers to the unsaturated air. And as this, let's say, as this volume of air, the parcel, this balloon goes up, so it would reach an altitude, a specific height, where there's lifting condensation level. It's called lifting condensation level. As the air lifts up to the sky, to the atmosphere up above, it reached the altitude at which a parcel reaches saturation and cloud formation begins. So this level, when the air reaches, it obviously, well, start to condense because by the name of it, like the lifting condensation level. So when it reaches the saturation, it begins to condense, and by this condensation, there is the release of latent heat. The latent heat that was absorbed by the water vapor, it was evaporated and released as sensible heat. If you remember the sensible heat, the heat that is measured by the thermometer, the heat that we can sense, that's why it's called sensible heat. This latent heat or the hidden heat was actually released, and therefore the air reached this altitude where it has become saturated now, and then there is this cloud formation that begins. That means there is a slow rate of cooling, because this slow rate of cooling of the saturated air is what we call the wet adiabatic rate. So the saturated, or it's also called as moist or saturated adiabatic rate. Because although this parcel of air will continue to cool adiabatically, but at this time, due to the release of latent heat, it slows down the cooling, and again, it's already saturated. Then we call this saturated adiabatic rate. The rate of the adiabatic cooling is called wet adiabatic rate or saturated adiabatic rate. Okay, now you see in this figure, in this graph, the lifting condensation level. So you can see in this, in the vertical axis, we have the height in meters, and from the surface, we have the 32 degrees Celsius temperature. And as you go up, as you can see, the rising air expands and cools. From 32 degrees Celsius, it has become 22 degrees Celsius. And from 22 degrees Celsius, as it goes up to another 1000 meters, it has become 12 degrees Celsius. So this expansion and cooling of air, let's mention that this is unsaturated air. This is what we call the dry adiabatic rate temperature. So this is what I've explained in the previous slide, but this is just the figure of showing it. So as it reached the lifting condensation level, here is the lifting condensation level. You noticed that from this level, there is the cloud formation that starts. So as the air continues to rise, again, the latent heat was released by this condensation. So it reduces the rate of cooling. And this is what we call the adiabatic, rather wet adiabatic rate. So again, the dry adiabatic rate is when the air is unsaturated, and after it passed through the lifting condensation level, it starts to condense, and the cloud formation has begun. And then this slowing of adiabatic cooling is what we call the wet adiabatic rate or the saturated adiabatic rate. And as what you, let's review. I've mentioned, let's review what is saturation really, because I think I've mentioned, even if I mentioned that in the previous topic. But okay, saturation occurs when the air temperature is the same as the dew point temperature. Do you remember the dew point, where the point where the air is starting to condense or starting to create or to produce this dew, and these results to the condensation or cloud formation. So that's where or how the saturation occur, because remember that most clouds most clouds are often formed when air rises and cools to its dew point, the dew point temperature. So this is the process of adiabatic cooling. So there is also another way of, or how this saturation occurs when the cool unsaturated air passes over a warm water body and sufficient water vapor is added below. So this is like this natural process is mainly responsible for the formation of clouds. So this is particularly this happens in over subtropical oceans. This is just example of, like, to give you the review or the idea of why air has become saturated or how saturation happens again. So as the air is saturated and it slows down the cooling, that's what we call the wet adiabatic cooling, and the rate is what we call the wet adiabatic rate. So now we're gonna go and check what are the mechanisms that causes the air to rise. So because we mentioned about rising of the air, and what are these mechanisms that cause the air to rise? First is what we call the orographic lifting. So this orographic lifting occurs when air is forced to rise over a mountainous barrier. And yeah, you can see in here that there is a picture, an example of orographic lifting in this green mountain. The orographic lifting leads to precipitation on windward slopes. And yeah, and there's also B. It's a process. The B, by the time it says here that by the time air reaches the leeward side of the mountains, much of the moisture has been lost, resulting in a rain shadow desert. So, as actually the air ascends a mountain slope because this orographic lifting occurs when their elevated terrain or the mountain acts as barriers to the horizontal flow of the air. So as the air ascends to this slope, adiabatic cooling often generates clouds and precipitation. So this picture is showing the orographic lifting and precipitation. And in letter B, this B figure, that means if the air descends, because after ascending, and then there is a barrier, and then as the air descends, uh, it warms adiabatically. So it's there's still the adiabatic warming and making condensation and precipitation even less possible. So in what you can see in the figure is the result that is almost like or called the rain shadow desert. Actually, if you noticed that from these two figures, there is actually the illustration above. So the wind blows the blue arrows. It blows horizontally, but then there's the barrier. Then it goes up, and then by the time it reaches the leeward side, so most of the moisture already has been lost. So this is like the Great Basin. That results to rain shadow desert. So another mechanism, we're still on the mechanisms of that cause the air to rise, is what we call the frontal lifting. So this frontal lifting is what you can see in here. There's still another lifting, yeah. It causes the air to rise. The warm air actually causes the air to uh, rise above the cold air. So this mechanism is happened when the warmer, less dense air is forced over cooler, denser air. So the colder, denser air acts as a barrier over which this warm water, or not water, warm air, or the less dense air rises. So warm and cold air masses often collide. And then these produce boundaries at what we call fronts. That's why it's called the frontal lifting. And these the weather-producing fronts are associated with storm systems called mid-latitude cyclones. And because these storms are responsible for producing a high percentage of the precipitation in the middle latitude because of this frontal lifting. So because of these fronts, the weather producing fronts, the weather that these fronts produce is mostly associated with a storm system that we called or termed mid-latitude cyclones, because these cyclones happen in the mid-latitude, and they are responsible for producing a high percentage of precipitation in the mid-latitude region. So another mechanism is what we call the convergence. So when the wind pattern near the Earth's surface is such that more air is entering in an area than leaving, so this is what we called the convergence lifting. So this is the horizontal flow of air that results in vertical lifting of air and cloudy conditions. And it's illustrated in here, the convergence. There is a vertical lifting because this horizontal flow of air, there is more entering, and then it converges at some point, and then it lifts up. So the inward flow of air at the surface of these systems is balanced by the rising air, or the cloud formation, is what you can see in here as it rises. The air is lifting the rising air, and then there is a cloud formation, and usually there's precipitation because of this convergence. And most often this convergence is associated with this mechanism of rising air is associated with large centers of low pressure. So these low pressure, if the previous mechanism is in the mid-latitude region, these low pressure, mainly the mid-latitude cyclones and hurricanes again. So convergence can also occur when an obstacle slows or restricts the horizontal airflow or the wind. For example, when air moves from a relatively smooth surface, such as the ocean, into an irregular landscape. So there is an increased friction that reduces its speed, and the result is like the piling up of air, or the convergence. So when air converges, there is an upward flow, of course, of the air molecules rather than a simple squeezing together. When they converge, they cannot just squeeze all together the air molecules, but they flow upward to find a way. When surface air converges, the column of air increases in height as what you see, it increases in height to allow for the decreased area it occupies. So there is an example here. Actually, Florida provides a good example in the map. You can see. On warm days, airflow from the Atlantic, here the Atlantic Ocean and the Gulf of Mexico, and they converge into the Florida Peninsula. So this generates, as what you can see, in the clouds, mid-afternoon thunderstorms. Because, well, as what I've mentioned, these commonly also occurs at the ocean, at the coast. Another mechanism is the localized convective lifting. So this localized convective lifting is the result of an equal surface heating that causes buoyant packets of air to rise. It is shown in this. For example, in the late morning, there is so much solar heating, and in the noontime, this heating starts to rise. The air starts to rise is what we termed as thermals. And so in the early afternoon, it has passed through the lifting condensation level. So this unequal heating of the Earth's surface causes this thermal rising, or the pockets of air to be warmed more than the surrounding air. That's why when it's warmed, it is less dense and it is buoyant. So if the hot air rise, they produce the thermals, and if they reach the lifting condensation level, the clouds form, and on occasion they also produce the mid-afternoon rain showers. So that is for the mechanisms that cause the air to rise. So now we've reached the topic of atmospheric stability. So when you say atmospheric stability, actually, clouds vary so much in size and shape, and this results to varied precipitation. Like the precipitation varied widely in space and in time. So this is what we call the stability of the air or the atmosphere. And when you say stability, this is what there is the term stable air. Stable air is if the parcel is cooler than the surrounding environment. Remember that if it's cooler, then it's more dense. And this kind of air, this type resists the vertical movement. That's why it's called stable air. And if there is unstable air, there is also unstable air. So this unstable air is the rising parcel, which is warmer, and therefore it is less dense than the surrounding air. So it will continue to rise as long as it's warmer compared to the surrounding air until it reaches an altitude where the temperature of this parcel is equal to the temperature of its surroundings. So the good example for this is the hot air balloon. So what do you think makes the hot air balloon goes up? It's because of the warm air inside, warmer air that it contains compared to the temperature of the air in its surroundings. So how is the stability of the air determined? So of course, the measure of environmental lapse rate. So the stability of the atmosphere is determined by regularly measuring the air temperature at various heights. And if you remember, the environmental lapse rate, the lapse rate that we discussed during the first topic, is the rate of change in the actual temperature of the atmosphere with height. So we discussed in the first topic that the lapse temperature, or the decreasing temperature with height, this is what we call the lapse temperature. But in general, it's not just the decreasing, but actually the rate of change in the actual temperature of atmosphere with height. So again, as determined from observations that is gathered through the radiosonde and aircraft. And yeah, I've mentioned this before. Again, the radiosonde is the instrument that we use to get the temperature of the atmosphere. And we've discussed so many things. You do not be confused with the environmental lapse rate and the adiabatic temperature changes, because the adiabatic temperature changes are the changes in temperature due to the pressure changes that a parcel of air experiences. Okay, so as this parcel of air moves vertically through the atmosphere, up or down, it changes the temperature due to the pressure. That's what we call the adiabatic temperature changes. But this environmental lapse rate is the actual temperature of the air, of the atmosphere. So what you can see in this figure is the environmental lapse rate of 5 degrees Celsius per 1,000 meter. So here, this is the environmental lapse rate of 5 degrees Celsius per 1,000 meter. So when this unsaturated parcel of air here is lifted, it expands and cools at the dry adiabatic rate, remember? Because this is the parcel of air. So at the rate of 10 degrees Celsius, because 25 to 15. So it cools down at a rate of the dry adiabatic cooling with a rate of 10 degrees Celsius per 1,000 meters. So in this example, the temperature of the rising parcel of air is lower than that of its surrounding. If you can see that the surrounding air is 20 degrees Celsius and the expanding air and the rising air is 15 degrees. So the rising air is 5 degrees cooler than the environment. So therefore, it's heavier. And if allowed to do so, there is a tendency that it will sink to its original position because it goes up again with a rate of 10 degrees from 25 to 15 to 5 degrees Celsius. Still 10 degrees Celsius in another 1,000 meters. So this is the adiabatic rate, and this adiabatic rate, as you can see, rather the rising air is cooler than the environment, then there is the tendency that it will sink down to its original position. And this is actually the environmental lapse rate that you need to check whether how is the stability of the air is determined is through the environmental lapse rate, and this is the in each parcel is the adiabatic rate. So you should not be confused with the two rates. So we've talked about the stable air, and I've mentioned that this will not rise unless forced to do so. So in this figure, you can clearly read that air parcel forced upward because the temperature of the parcel of the air and the surface temperature is the same. That means the air is stable because this parcel of air is not denser, nor it is less dense. Because if this parcel of air is less dense, then you would understand that it's buoyant and it could raise, but then it's the same temperature with the environment, the surface temperature. That means the air is stable. So this example is there is something that forced the air to rise, and by nature this force is commonly through or by frontal lifting. So again, this is the temperature of the environment. That's the temperature of environment is what you measure through the with the environmental lapse rate. That's the stability of the air is determined. And there's actually the fundamental conditions of the atmosphere. So these fundamental conditions include absolute stability and absolute instability, as well as conditional instability. So we're going to go through one by one to these three fundamental conditions of the atmosphere. So what is absolute stability? Accordingly, this absolute stability prevails when the environmental lapse rate is less than the wet adiabatic rate. We've already known the difference of environmental lapse rate and the adiabatic rate, which we should not be confused. So in this figure, you can see that in this vertical axis is the height in meters, and there is in this the red arrows indicated the dry rate of the adiabatic cooling, and the wet rate is in the above blue arrows of the adiabatic cooling. And so sorry, excuse me, and this parcel of air is always cooler and heavier than the surrounding air. That's why it produced stability. So again, this stability or absolute stability prevails when the environmental lapse rate, this is the environmental lapse rate that we can find in here, is less than the wet adiabatic rate. This is the wet adiabatic rate. So as what you can see, this rising air is always cooler and heavier. So rising air is 5 degrees Celsius cooler, and then 10 degrees cooler, and 11 degrees cooler, and 12 degrees as it goes up. So it's always more dense and heavier than the surrounding air temperature, which is 15 degrees, 10 degrees, 5 degrees, and 0. So that's why it is called stable, because it does not go up, not unless it is forced to go up. So again, when the environmental lapse rate is less than the wet adiabatic rate, the air exhibits absolute stability and it resists vertical movement. So if this stable air is forced above the lifting condensation level, here is the lifting condensation level. If this air is forced, as it was shown here, forced to go up, then you can see a flat widespread clouds. So these flat widespread clouds is generated. And also precipitation, if sometimes it happens, will be light to moderate. It depends on the moisture content of the air. So this is what we call the absolute stability. Next is the absolute instability. It's the opposite. So absolute instability happens when the environmental lapse rate is greater than the dry adiabatic rate. So now the environmental lapse rate should be bigger or greater than the dry adiabatic rate. So that's why it produced the unstable air. So this figure in here, the A figure, the absolute instability can develop when solar heating. This solar heating causes the lowermost layer of the atmosphere to be warmed to a much higher temperature than the air above. So it's 40 degrees Celsius in here, and then the result of this is a steep environmental lapse rate, and it makes the atmosphere unstable because it's too much heat from the sun. The environmental lapse rate is very steep, or it's very high, and it's making the air unstable. So why is it making the air unstable? Because let's say when the environmental lapse rate is greater than the dry adiabatic rate, the environmental lapse rate that you can see in here is 12 degrees per 1,000 meters. It's very steep, it's very high because in the surface it is very hot because of the sun. Then it is, as it goes up, the decrease is steep. So this environmental lapse rate is greater than the dry adiabatic rate, which is only 10 degrees Celsius. And the air exhibits absolute instability. The air is not stable because of its buoyancy. Because if this air is buoyant, since it's the rising air is warmer than the environment, then it's buoyant and it will go up, and it could actually produce a severe weather. And convective lifting of the air near the Earth's surface, it generates towering clouds, and as what you can see here, the potential of mid-afternoon thunderstorms. But also it tends to dissipate after the sunset because it has something to do with the solar heating. So again, in this illustration, this parcel of air is less dense. That's why it's buoyant. The rising air is 2 degrees warmer than the environment. That's why it goes up. That's why it's unstable, because it's rising up. And it's making this dry adiabatic rate lower than the environmental lapse rate. So this is what we call the absolute instability. And now the last is we have the conditional instability. So this is a common type of atmospheric instability. And this situation prevails when moist air has an environmental lapse rate between the dry and wet adiabatic rates. So between 5 degrees Celsius and 10 degrees Celsius per 1,000 meters. So when moist air has an environmental lapse rate between this dry and wet adiabatic rates, it exhibits conditional instability. If this air is forced to go up, it has the potential to become unstable and produce severe weather. So again, what do you mean by the situation that prevails when moist air or the saturated air has an environmental lapse rate between dry and wet adiabatic rates? It means that when the atmosphere is actually unstable when it is stable with respect to unsaturated parcel of air, but unstable with respect to saturated parcel of air. Okay, to visualize this, this conditional instability that you can see may result when warm air is forced to rise along a frontal boundary. So here you can see that the environmental lapse rate is 9 degrees Celsius per 1,000 meters. It lies between dry and wet adiabatic rates. The dry rate is 10 degrees Celsius and the wet rate is 9 degrees Celsius. So a parcel of air is cooler than the surrounding air until around this area, 2,500, let's say 2,500 meters. So where there is tendency, the tendency is to sink toward the surface. There is a tendency to sink because the rising air is cooler than the environment until the 2,500 degrees. So above this level, 2,500 meters and above, the parcel of air is warmer than its environment, and it will continue to rise because of the buoyancy. So thus, when conditionally unstable air is forced to rise, this result is what you can see, the towering cumulus clouds. So this is, in the B, is just a graphical representation of conditions shown in the A. And actually, because of the release of latent heat that occurs above the lifting condensation level, here is the lifting condensation level, the parcel of air becomes warmer eventually than the surrounding air. That's why from here it's cooler, and then as it reached this level of convection, of free convection, so it releases latent air, and then it becomes warmer. So this altitude, or the level of free convection, this is the altitude at which air rises because of its own buoyancy. And until then, so from there rather, the air rises because it has become buoyant. So continuing to discuss about the conditional instability, as what we've seen, that cloud continues to go up in the previous figure. However, it does not continue to grow indefinitely, because when conditionally unstable air is lifted above the lifting condensation level, we've seen the result with the towering thunderstorms, let's say here. But it stops in this level because at what actually in this example, you remember that stratosphere, the air temperature increases with altitude due to sunlight absorbed by the ozone. So this stratosphere forms a warm inversion layer, if you can still remember our previous topic, caused by the solar heating of ozone. So in the first topic, the stratosphere actually is a temperature inversion layer of air in which the temperature increases with altitude, and therefore it serves as a lead, or to stop the growth of towering clouds. So this level inhibit the cloud growth. So that's why the cloud does not continue to go up. And there is what we call the equilibrium level. So this equilibrium level is the level where the rising parcel becomes colder than the environment. So you can see here in this graph, this is the equilibrium level. So the region of instability and free convection that we've mentioned that exist, it only exists until the yellow line that represents the temperature of the rising. Here, the yellow line represents the temperature of the parcel of air. This region of instability and free convection is only until this yellow line intersects with this red line, or what represents the temperature of the environment. So at this point, that's what we call the pressure. At this pressure, the red one, the temperature of the rising parcel is again equal to its surrounding, and it's causing the parcel to lose the buoyancy, and that's why it has stopped going up. So it's what we called the equilibrium level. And this left figure and the right figure is actually the illustration of each other, the reflection of each other. In the right figure is just a graph. In this level, the equilibrium level is where the temperature inversion occurs, and then where the inhibition of cloud growth starts. So it theoretically stopped the top of a growing thunderstorm. And now we will see how the stability changes. So instability is actually enhanced by the following. So first, instability is enhanced when there's a warming of the lowermost layer of the atmosphere by solar radiation during daylight. We've seen that. Well, that's why there is absolute instability happened, because of too much warming of the surface layer of the earth by the solar radiation. And also instability is enhanced by heating of cold air mass from below as it passes over a warm surface, or bringing in warm air near the surface, or the warm air advection. And also the upward movement of air caused by processes such as orographic lifting, Brunton lifting, or convergence. So we've already seen this, and the radiation cooling of cloud tops, as what we've just seen in the previous slide. And now here, because we're talking about the changes of stability and how it really happens, we have instability and now the stability. So the stability is actually enhanced when there's a radiation cooling of Earth's surface after sunset. So the Earth's surface is starting to cool, and the air is starting to be stable. And the cooling of an air mass from below as it traverses a cold surface, or the arrival of cold surface air, or called the cold air advection. So it's the opposite of the warm air advection. And then another is the subsidence, or the general downward flow of the air. Actually, when there is a general downward flow of the air, the upper part of the column of the air, let's say, is heated because of the compression, because as it goes down, there's a downward flow. The upper part is compressed, and usually the air above the surface, that means in the bottom part, is not involved in the subsidence, because actually the ground inhibits sinking motion, so its temperature remains unchanged. That's why in the subsidence only the upper part of the air is compressed, and this compression produce heat, and because this air that is compressed is warm more than the air near the surface, then subsidence or the general downward flow of the air tends to stabilize the atmosphere. So again, this is just the illustration or the summary in total of the overall atmospheric stability. We have the three different types: the absolute stability, absolute instability, and the conditional instability. And there, its atmospheric conditions. That absolute stability means, or it occurs when the environmental lapse rate is less than the wet adiabatic rate, and absolute instability occurs when the environmental lapse rate is greater than the dry adiabatic rate, and the conditional instability occurs when moist air with an environmental lapse rate between the dry and wet adiabatic rates. So here you can also um, determine the associated weather of these atmospheric stability, and then it illustrates in the right side how is this happened. And now we have cloud formation. So for cloud formation, clouds actually consist billions of minute water droplets and or ice crystals that are suspended above the Earth's surface. So we all know that clouds provide a visual indication of the atmospheric conditions. For condensation to generate clouds, actually the air must reach like a saturation, and there must be a surface on which the water vapor can condense to form these liquid droplets that consist the clouds. So, these when the condensation occurs above, the tiny particles known as the cloud condensation nuclei serve as its purpose. So the clouds, um, for the condensation of the rather to generate the clouds, there must this a surface, and these cloud condensation nuclei serves that purpose. And then from the cloud droplet growth begins on cloud condensation nuclei. And it takes about 1 million cloud droplets to form a single raindrop. And these condensation nuclei are actually the most effective particle for condensation above the air, or the atmosphere rather, are hygroscopic nuclei, or the water-seeking nuclei compared to the hydrophobic, or the water-repelling ones. So these hygroscopic nuclei, or what we call the water-seeking nuclei, so when this exposed to the humid air, they absorb moisture. So that's why they are water-seeking. They are called water-seeking. For example of this is over in the ocean, there is the salt particles. There are salt particles that are released into the atmosphere when sea spray evaporates. And because salt is hygroscopic, water droplets begin to form around salt particles. So that's why, let's say, these water-seeking nuclei is most effective particles for condensation, rather than this hydrophobic, or the water-repelling, that are not efficient condensation nuclei. Although even if they are not efficient condensation nuclei, but cloud droplets could also form on this nuclei when the relative humidity reaches 100%. But it's not that effective comparing to the water-seeking or the hygroscopic nuclei. And what are these sources of condensation nuclei? So first is the dust forms, particulates from volcanic eruption, and then we also have pollen from plants, and it could also be introduced to the atmosphere through the byproducts of combustion or burning, like the forest fires, automobiles, or the coal burning furnaces. So now we're gonna check the cloud classification. As what you can see in here, this is the general cloud classification that we are using for the present day, because in 1803, there's an English naturalist named Luke Howard who published a cloud classification scheme, and this serves as the basis of our present day system. So this Howard system classifies clouds on the two criteria based on form and height. So in general, this is like the scheme of like the summary of all this cloud classification, and we're gonna go through them one by one. So first, check the cloud forms. So clouds are classified based on how they appear when viewed from the Earth's surface. So there are three basic forms or shapes. First is the cirrus, or the cirriform. This is the thin or wispy. From the Latin, cirrus is from the Latin word meaning for curl or filament. So these cirrus clouds form delicate veil-like patches or wisp-like strands and often have feathery appearance. And next is we have cumulus, or the cumuliform, or the globular masses. This is heap or pile in Latin. And these clouds consist of globular cloud masses that look like cotton balls or sheep in the sky. And the third one is the stratus or the stratiforms. That means sheets or layers. So these consist of sheets or layers or the strata that cover much or even entire the sky. So we're gonna check them one by one later. And actually, all clouds have at least one of these three basic forms, and some are a combination of two of them. For example, is like the stratocumulus. So the stratocumulus clouds are mostly sheet-like structures, and so this stratocumulus, sheet-like structures, and it's composed of long parallel rolls and broken globular patches. Another is, in addition to the term, is actually the term nimbus. It's from the Latin for violent rain. It is used in the name of a cloud that is major producer of precipitation. So these are the cloud forms. For example, aside from the stratocumulus, that is a combination of two of these forms, we also have the nimbus stratus. So this denotes a low, relatively flat rain cloud, whereas cumulonimbus describes a puffy, tall rain cloud. But anyway, we're gonna check them how they look like in pictures. So the second criterion of classifying clouds is the height. Aside from the form, the second one is the height. So it recognizes three levels. First is the high clouds. So these high clouds form the highest and coldest region of the troposphere and normally have bases above 6,000 meters or 20,000 feet. And these clouds are at the temperatures rather of these altitude are usually below freezing. So the high clouds, since the temperature is below freezing, these high clouds are generally composed of ice crystals or super cold water droplets. And the next one, based on height, is what we call the middle clouds, or these occupy the heights from 2,000 to 6,000. So these may be composed of water droplets or ice crystals also, depending on the time of the year and temperature profile of the atmosphere. And the third one is or are the low clouds. The low clouds form nearer to Earth's surface, up to actually an altitude of about 2,000 meters. So it becomes closer and closer to the surface of the Earth. And these low clouds are generally composed of water droplets. So, except winter, these low clouds are not composed of water droplets, but only in winter. So actually these altitudes that is specified in here may also vary somewhat depending on the season of the year, and also latitude. Depends on which latitude the clouds is forming. And another one, the term of the clouds that seem to be extending upward to span more than one height range, is what we call the cloud of vertical development. So if there is a cloud that expands upward to more than one of these height range, then that's what we call the cloud's vertical development. So we're going to check, again, as what I've mentioned, we're going to check how these clouds look like. And first, we're the high clouds. So these high clouds actually have three basic cloud types. So first is the cirrus, next is the cirrocumulus, is the B, the cirrocumulus, and C is the cirrostratus. So the cirrus clouds in this picture, the clouds with hooked filaments are called mare's tails. Looks like the tail of the mares or the horse female. So, and in the next picture, in the B, is the cirrocumulus. This is the cirrocumulus clouds, and in this picture, it shows small globules that resembles fish scales, or commonly called mackerel sky if this happens. So the cirrocumulus clouds appear as white patches composed of small cells or ripples. And next, below here, this is what we call the cirrostratus. So the cirrostratus is actually, they can be recognized easily when they produce optical effects such as halos around the sun or moon, as what you can see in the picture, as what you can see in this figure. So they are commonly transparent, whitish cloud that veils with a fibrous or sometimes smooth appearance that may cover much or all of the sky. So occasionally they are very thin and transparent that they are barely discernible. And also an important trivia for these cirrocumulus clouds. So they may warn of impending stormy weather, the cirrocumulus clouds, because this observation has given rise to an old mariner's phrase that mackerel scales and mare's tails make lofty ships carry low sails. That means, as a mariner, it brought you these types of clouds. It brought you low sails. So it has still something to do. That's why we're talking about the meteorology, because of course it has something to do with the ocean and with the mariners and even the fisher folks. So next is the middle clouds. So these middle clouds found in the middle altitude range. That's why it's called middle clouds. And this is described with the prefix alto, meaning middle. And this includes the altocumulus, which is here in the first picture. This is the altocumulus. Tends to form in patches composed of rolls or rounded masses. So this happens because, or it looks like this, because they are generally composed of water droplets rather than ice crystals. So the individual cells usually have more distinct outline. And altocumulus are sometimes confused with the cirrocumulus, which are smaller and less dense, and stratocumulus, which are thicker. But they are commonly confused, but altocumulus also is called altocumulus. It's because where it is formed in the middle of the atmosphere, middle height range. And next is the altostratus. So in this one, in the second figure, is the altostratus. These occur as grayish sheets covering a large portion of the sky. So when visible, the sun appears as a bright spot through these clouds. So it's just like the sheets covering the large portion of the sky. And unlike what we see with cirrostratus, these altostratus do not produce halo. Because with the cirrostratus, we've seen the halo, and this one does not produce the halo. So infrequent precipitation in the form of light snow or drizzle may also accompany these clouds, and they are commonly associated with approaching warm fronts that may thicken into a dark gray layer of nimbostratus clouds capable of producing steady continuous rain or even snow during winter. So those are the middle clouds. Now, yeah, we're going to check the low clouds. So for low clouds, there are three members of the family of low clouds. That's the stratus, stratocumulus, and nimbostratus. So stratus, these are the clouds. Stratus clouds have uniform bases and appear to blanket the entire sky. So they form in low horizontal layers that on occasion may produce light drizzle or mist. So they are white to gray in color. And you can see in this picture, this is a satellite view of a large bank of stratocumulus clouds over the Pacific Ocean, just south of San Diego, California. So this is the stratocumulus clouds that commonly form over mid-latitude ocean, because stratocumulus clouds cover such large areas. They are extremely important for the Earth's energy balance. So primarily because they reflect considerable amounts of incoming solar radiation. That's why. And another is the nimbostratus. So this picture here, these dark gray layers, this is what we call the nimbostratus. They often exhibit a ragged appearing base, and this derived name from the Latin word nimbus, or that means rain cloud, and stratus, that means to cover with a layer. And nimbus stratus, these are the clouds that are significant precipitation producers. So for the low clouds. And now we've mentioned about the clouds of vertical development, right? So the most familiar type of these clouds is the cumulus clouds. First, focus on the picture in the left side. This is the cumulus clouds. It is often called fair weather clouds. So clouds having their bases in low height range and extending upward into the middle or high latitudes are called clouds of vertical development. And cumulus clouds are the most familiar type of clouds of vertical development because it most often form on clear days when unequal surface heating causes the parcel of air to rise convectively above the lifting condensation level. And again, Um, they are often called fair weather clouds, is what you can see in here. So as what you can see, this is the small cumulus clouds, or what we call the cumulus humilis. So these fair weather clouds rarely produce appreciable precipitation. So this cumulus cloud could also grow, because when the air is unstable, cumulus clouds can grow dramatically in height, and its top enters the middle height range. And this is what we call the cumulus congestus. So this cumulus congestus is when the cumulus the top enters the middle height range. And if the cloud continues to grow, then it's called cumulonimbus. If it becomes cumulonimbus, that means the cloud continues to grow and the rain begins to fall. And this, as shown in this picture, is the dense billowy clouds and have a great vertical extent and can produce heavy precipitation or amount of rain and violent thunderstorms. So for cloud varieties, actually, the 10 basic cloud types that we've seen can be further subdivided into varieties that are named using adjectives that describe the particular cloud characteristics. For example, here is the lenticular clouds. So here in the first picture, these lens-shaped clouds are relatively common in mountainous areas. That's why it's called lenticular clouds, because it's lens-shaped clouds. So the formal name of lenticular clouds is Altocumulus lenticularis. So they are common in rugged or mountainous topographies, and as moist, stable air passes over this mountainous terrain, a series of standing waves form on the downside, as it's shown in this figure. So this diagram depicts the formation of lenticular clouds in turbulent flow that develops in the lee of the mountain range. So as the air ascends, the wave crest, it cools adiabatically. So there's an adiabatic cooling again that happens. So if the air reaches its dew point, then that means it forms the moisture in the air. The moisture in the air will condense to form a lenticular cloud. So as the moist air moves down into the throat of the wave, as what you can see here, the cloud droplets evaporate, so leaving areas with descending air cloud free. And another term that describes for these cloud varieties is actually when stratus or cumulus clouds appear broken or fractured, and this adjective fractus is used in their description. So also the term mammatus, it's applied when some clouds have rounded protuberances on their bottom surfaces, similar to a cow udder. And another one is the term oncinous, or it means hook shape. This is applied to streaks of cirrus clouds that are shaped like a comma resting on its side. For example, is the cirrus oncinus are often precursors of bad weather. And for the continuation, I will upload the next video for the cloud precipitation and how it forms and its type and how it is measured. So for the continuation of this topic, we still have how precipitation forms. That means the precipitation process and including its type, and how precipitation is measured. We're gonna talk about that in the next video that I will upload. That will be the part 2 of the 4th topic of our class. And so to sum up the first part of our lecture for today, these are the points that you need, some of the points that you need to remember. The highlights where when the air expands, it cools, and when the air is compressed, it warms. And the temperature changes produced by means of changes in air pressure, in which thermal energy is neither added nor subtracted, are called adiabatic temperature changes. And stable air resists vertical movement, whereas unstable air rises because of its buoyancy. And when stable air is forced aloft, relatively thin widespread clouds typically form, and any precipitation that results is light to moderate. In contrast with that, as unstable air rises, towering clouds are generated that are usually accompanied by heavy precipitation. And clouds form in the atmosphere when water vapor condenses on cloud condensation nuclei. And so that would be all for today. Thank you so much for your attention and for listening. Have a nice day.